Hello friends, I am Gaurang Makwana. I welcome you all to my another video tutorial Biotech guide. So in this video lecture we are going to discuss about Michaelis-Menten equation, which is a very important topic in enzyme engineering theory. So in this video lecture we are going to discuss about first why Michaelis-Menten equation is important and how it came into enzyme engineering theory. Then second, how Michaelis-Menten equation is defining as steady state kinetics or mixed order kinetics. So first question answer is available in this video. So stay tuned and enjoy this video lecture. So let us discuss first why Michaelis-Menten equation is defining as a steady state kinetics or a mixed order kinetics. So first, as we know, substrate react with enzyme and then make it a complex known as a substrate enzyme complex. That stage is defining as a transition state. After that, that substrate enzyme complex is further converted into the product and the free enzyme. Now, we assume three assumption. First is low concentration of substrate, second is medium concentration of substrate, and the third is a high concentration of a substrate. Let us see first low concentration of a substrate. So here you can see when the substrate concentration is low, few enzymes are unoccupied. At that time, product concentration is increased, which is defining as a dc by dt. Here dc by dt is defining as a rate of reaction. That is also called as a velocity of a reaction. So when the rate of reaction is increased, velocity of reaction is also increased. So when we plotted a graph between a velocity of a reaction and a substrate concentration, we'll get it linear in the form. So we'll also defining as a dc by dt is proportional to concentration. Why? Because the concentration is increased, at that time the rate of reaction is also increased. So this case is also defining as a first order kinetics at the low concentration of a substrate. Second, medium concentration of the substrate. When the substrate concentration is medium, many enzymes are occupied, concentration of the product is also increased. At that time, rate of reaction is also increased, dc by dt. But when plotted down a graph between a V versus S, we will get a non-linearity. Here you can see this is the non-linearity. That's why we will defining them a minus dc by dt is not proportional to a concentration, which is known as a mixed order kinetics. So here Michaelis-Menten equation came. Third condition, high concentration of the substrate. As we know, enzyme having a fixed capacity, so at the time of a high concentration of the substrate, all enzymes are occupied and other are remaining. So at that time, the product concentration is increased, but the rate of reaction dc by dt is not increased. So at that time, when we plotted a graph between a V versus S concentration, will get it this type of linearity, that is known as a plateau, and also we having a constant velocity. So minus dc by dt here we defining as a maximum velocity. So minus dc by dt is equal to Vmax, maximum velocity. Let's revise three condition. When the substrate concentration is low, the graph between velocity and the substrate concentration is in the linear in the form, which is defining as a first order kinetics. Second, medium concentration of the substrate will get a non-linearity, which is also defining as a mixed order kinetics. And at the third, high concentration of the substrate will get a plateau in the phase and a maximum velocity, which is defining as a zeroth order kinetics. Let us come on to our topic, Michaelis-Menten derivatives. As we know, enzyme react with a substrate or make it a complex enzyme substrate complex, which is a forward reaction, and here we put it a K1, which is a forward reaction constant. This enzyme substrate complex further going revert back and release substrate and the free enzyme, which is defining as a K-1 reverse reaction constant. Now further, otherwise if enzyme substrate complex is going to in the forward position, what happen? Releasing the product and the free enzyme, which is we defining as a K2. We apply steady state approximate of these two equation. dEs by dt is equal to K1 enzyme concentration into substrate concentration minus K minus 1 into enzyme substrate concentration. Why we put here minus? Because the reaction is going into the back reverse position, that's why. Then minus K2 into enzyme substrate concentration is equal to 0. Now here you can see enzyme substrate complex ES is will get it into the common. Okay, so what will get? dS by dt is equal to K1 E S into S, then minus K minus 1 plus K2, because the minus and minus converted into plus. So here K minus 1 plus K2 bracket close, and we'll get it ES as common and is equal to 0. So here we considering this equation is the first equation number 1. Then now we apply enzyme conservation law. So total enzyme concentration is equal to enzyme concentration plus enzyme substrate complex concentration. So here we need enzyme concentration, so we take it out from the left side E, then what will get is equal to total enzyme concentration E0 minus ES. So here we defining this equation is a equation number 2. Now we put it this equation number 2 into equation number 1. So what will get? dEs by dt is equal to K1 in bracket E0 minus ES bracket close into substrate concentration minus K minus 1 plus K2 bracket close ES. So we multiply them. K1 E0 S minus K1 ES into S minus K minus 1 ES plus K2 ES. So here ES is common at the end, so ES we take it is a common, and K1 E0 S will take it from the left side. So K1 E0 S is equal to K minus 1. Here we change the symbol because the K1 E0 S is when going into the left side they goes into the minus, but here we change it that symbol. So that's why the K minus 1 plus K2 K1 S bracket close and ES. So here we defining this equation in the equation number 3. We write it down this equation number 3 into this form. ES is equal to K1 E0 S divided by this all whole K minus 1 K2 plus K1 S is going into a division form. So our perfect equation is ES is equal to K1 E0 into S divided by K minus 1 plus K2 plus K1 S. So this is our fourth equation. So now a rate of formation of a product defining as a R. So R is equal to D product concentration dt is equal to K2 ES. So here number of fourth equation value will put it into this number of 5 equation. So what will get? K1 K2 E0 S divided by K minus 1 plus K2 plus K1 S. So this is our number of 6 equation. Now we will divide this equation by K1. So K1 K2 E0 S divided by K minus 1 plus K2 divided by K1 and plus K1 S divided by K1. So here these all K1 are removed and we'll get it. Our final equation R is equal to K2 E0 S divided by K minus 1 plus K2 divided by K1 and plus substrate concentration. This is our equation number 7. In equation 7, K minus 1 plus K2 divided by K1 is also defining as a Km Michaelis-Menten constant. So what will get? R is equal to K2 E0 S divided by Km plus S. This is our final equation number 8. Here K2 E0 is defining as a total enzyme concentration. At the total enzyme concentration also we'll get it a maximum velocity of the reaction, and R, which is a velocity, also defining as a velocity, rate of reaction is equal to velocity of the reaction. So what we'll get here, V0 is equal to Vmax into S divided by Km plus S, which is our final Michaelis-Menten equation number 9. Now let us come back to our first three hypotheses: first order, mixed order, and zero order kinetics. So let us discuss first order kinetics. At the low concentration of the substrate, we'll define Michaelis-Menten equation in the form of V is equal to Vm into C divided by Km plus C. Here we'll define substrate concentration in the form of a C. So in case of a low concentration of the substrate, the concentration is product concentration is low compared with the rate of a reaction. So here we write it down, C is less than the Km value. So here Km plus C is also, we considering them a Km because the concentration of the product is low, so is negligible. So Km plus C will defining them a Km. So we'll put it down this value here in the equation. V is equal to Vm into C divided by Km. Okay. And here Vm divided by Km is also defining as a K. So what we'll get here, V is equal to K into C. Now second, mixed order kinetics. So in mixed order kinetics, medium concentration of the substrate, both concentration and the Km is significant, so not as such differentiation is there. V is equal to Vm into C divided by Km plus C. Third, zero order kinetics. At the high concentration of the substrate, what will happen? V is equal to Vm into C divided by Km plus C. At that time, concentration of the product is high compared with the rate of a reaction, which is a very low. So here we defining as a C greater than the Km value. So here we defining Km plus C is proportional to the C. So we'll put it this value into the equation. So what we'll get, V is equal to Vm into C divided by C. So here we also consider as V is equal to Vm at the maximum velocity. Now let us discuss few application of this equation: in vitro, in vivo, and in situ processes. The equation is used to explain the kinetic of all the processes. Then the drug development. Enzyme inhibition studies help understand reaction mechanism, which is important for a drug development. And other topics, the equation has also been applied to topics such as alveolar clearance of a dust, clearance of a blood alcohol, and a photosynthesis irradiation relationship. So here are the application of this equation, and we completed our topic Michaelis-Menten derivatives, also defining as a steady state kinetic equation, kinetics of enzyme catalyze process, and the mathematical reaction between a V0, Vmax and the Km for a first order and the zeroth order kinetics. So here we completed our video. I hope you enjoyed very well and got it very well. Thanks for watching, and if you want to get more videos regarding like this, join with us, subscribe to our channel, press the bell icon, never miss an update. Thanks for watching.